Dear students, welcome back. All of you are enjoyed your vacations. This is the time to come back for our academics. You are entered to 7th semester. So this time I am going to take you the subject Power System Analysis 2 17E71. In the previous semester, you have studied the subject called Power System Analysis 1, where you have studied single line diagram of a network, impedance diagram, reactance diagram, sequence networks, fault analysis, many things you have studied. So this is a continuation of the subject where here in this subject we are going to learn more about the computer techniques in this power system analysis. So a major thing in this subject is we are going to make the mathematical models. By that we can analyze the power system to get the required line forecasting, voltage, as well as currents, power, everything. Let us start with the subject. What is a power system? Yeah, you come across these things from the many subjects like power generation, transmission, distribution. An interconnected electric network which makes available electric power generated by the generating plants to the load through the transmission and distribution networks. As you know, power is generated at the generating stations, usually which is located at the remote places. So from there, we are going to generate the electric power, and it will be transmitted through the transmission lines. Then once again, it is distributed through the distributed networks. In this, we will see the generators, transformers, transmission lines, which yes, many things are coming in this network. So it's a combination of many equipments togetherly become one power system. So we will see this subject at a glance. What we are going to study in this subject. The first one is the network topology. So like that, in the previous subjects you have studied the reactance diagram. From the reactance diagram we are going to get the graphs of the particular power system. So from the graphs we will get the oriented graphs, tree, co-tree, subgraph, like the many things we are going to find. So that is coming under the network topology. Then coming to the network matrices, where we can find the bus impedance matrix, primitive matrices, as well as cut set matrix, as well as the loop matrix. So these matrices are help us to find the current buses, voltage buses, or find the complex powers using this matrix. The next one is the load flow studies, the important part of this subject where we can find the line flows, power flows using these studies. And the next one is the optimal system operation. So optimal system operation is mainly deals with the sharing of the loads, or a system is connected with the more than one generators, how these generators are to be loaded, equally loading as well as economically loading. There is the two different things. Equal loading of generators may not be result in the economic one. So to get the efficient economic results, we need to go for the optimal system operation. Then we need to study the symmetrical fault analysis as well as power system stability. So let us see what is computer application in power system, or what are the different steps we can see in the computer application in power system. Defining the problem and objective. At the very first, we need to define the problem and what is the objective, what is we are going to achieve, or what is exactly the problem we are going to facing, that we need to define the first. The next one is assessment of data available and preparation of input in proper format. So many data are available with us, like generator details, bus details, many things will be available, or type of bus. So these things we need to prepare in the proper format which can be used as an input. Next is development of a mathematical model. Yeah, once we are ready with our data, we can go for modeling a system. So this is what the very important step where we can going to develop the mathematical model. Then once the mathematical model is ready, then we are going to select the suitable techniques. Which techniques we are going to choose for solving this particular problem. To solve this particular problem, we need to have a flowchart or algorithm. How to solve this, or what are the things to be taken first, what are the things to be executed next. These priorities can be given. So once these things are ready with our flowchart and algorithm, we can develop a computer program, or we can write the program to solve our problems. So what is elementary graph theory? The geometrical interconnection of the various branches of a network is called topology of the network. So from the reactance diagram, we are going to get the graph of a particular network, and this is nothing but a geometrical interconnection of the various branches of a network. So the connection of the network topology shown by replacing all its elements by line is called a graph. So main thing is, what is graph and what is a network? What is the difference between these two? So graph is obtained from the network only. This network might be having number of transmission lines, number of transformers, many other equipments, but all those elements are replacing by a line. This is called as a graph. The linear graph consists of a set of objects called nodes and other set of called elements, such that element is identified with an ordered pair of nodes. The one element is usually terminates at a node, or one element is connected between two nodes. An element is defined as any line segment of the graph irrespective of the characteristics of the component involved. Either it may be a transformer or a transmission line or a generator. We will define as a line segment. A graph in which the direction is assigned to each element is called oriented graph or directed graph. Usually this direction is given with respect to the flow of current. So when a graph is directed with the direction of current flow, that is called as oriented graph. Elements are indicated by numbers and the nodes are by encircled numbers. Usually we will practice this method here. That is what the elements are given by its numbers, like 1 2 3 4 till n, and the nodes also given with the same numbers but which is encircled, and the usually the ground node is taken as the reference node. So in this figure we can see a 3-bus network. So this is a single line diagram. The encircled numbers you can see there, 1 2 3, these are the buses, and where you will see the green color, that is generators, which is connected to each bus. So we can conclude that generator is connected between one bus and another end is connected to ground. So which is not shown here, but we need to conclude that the generators one end is connected to ground. Means here 3 generators are there. All the 3 generators are connected to ground by other end. So this single line diagram we will replace with the reactance diagram. See here, the same diagram which I have shown in the previous slide, from the same figure I got here a reactance diagram. So see, you can see here 1, 2, 3 numbers with the yellow and encircled. These are the nodes. Usually in this reactance diagram, nodes are denoted by a dots. These dots are connected with the reactances of the each element. And once again, you can see, I told you in the previous slide only, 3 generators are connected, other end is connected to ground. You can see the difference clearly here. The generators, all the 3 generators are connected to the ground, where it is shown by 0 with encircled one, and remaining lines are shown with its reactances. See, from the reactance diagram, we are shown here oriented graph. See, reactances, whatever I have shown with its reactors, now it is replaced by single lines. And you can see here 1, 2, 3, then 4, 5, 6. So 1, 2, 3 is in straight lines, and remaining 4, 5, 6 is in dotted lines. The straight lines are called as branches, and the dotted lines are called as links. What is the difference between these branches and links? Even though it is elements, we are calling it as a branch as well as links. Why it is called as like that? See here. So we will go for the connected graph. This is the graph where at least one path exists between any 2 nodes of the graph. Means there might be number of nodes present in a network, but minimum one path should be. Path means the direct connection should be available from one node to another node. A representative power system can be a system, and its oriented graphs are shown in the previous figure I have shown, from where we can take E is equal to number of elements. See here, 1, 2, 3, 4, 5, 6. 6 elements are there. Same thing I have taken here. E is equal to 6. N is taken as number of nodes is 4. See, 1, 2, 3, and one other one is reference node 0. So totally there are 4 nodes. Fine. Then number of branches. Number of branches is given by total number of nodes minus 1. Means excluding reference node, how many number of nodes are present, that many numbers of branches will be there. Then what about the links? Links are nothing but total elements minus branches. So we can give the numbers such a way that the first elements are the branches, and the last elements we can take it as a links. What is subgraph? SG is a subgraph of G. See, G is a graph which is whichever we have seen in the previous diagrams. So SG is a subgraph of the particular G, where these conditions to be satisfied. The first one is SG is itself a graph. A subgraph is itself a graph, and every node of SG is also a node of the graph. Means a subgraph, every node also a node of the main graph, and every branch of the subgraph is a branch of graph. And what is loop? A subgraph L of the graph G is called as loop, and the L is a connected subgraph of the G, as well as preciously 2 and not more or less than 2 branches are incident on each node in L. Means one loop has to connect only one link. Number of branches may be more than one, but one loop should contain only one link. So this is what the introduction about this graph theory, as well as what is topology of electrical network. So in the coming classes we will see in detail of this subject, how we can use the computer techniques in this power system analysis. Thank you.